to start again, and we're starting the second session this afternoon with people from this university. Antonio has a postdoc overview. He has finished a PhD in theoretical physics in Valencia and worked in Dublin and in Nijmegen, Amsterdam. And Alex has just finished a master's in French and a master's in history and philosophy of science here at Utrecht University. And they will talk about scalar.
Thank you, Tanya. So this will be this is part of the master project as Niels explained, and we will focus on the scalar-tensor theories, but this is an ongoing work in progress topic, so we are expecting criticism and opinions of all kinds. This is not closed at all, but hopefully we can briefly explain what we have been doing this past year and a half on that. So I did a bit theme of what's the idea of the presentation because I tend to forget but in which part we are going at each step. So basically what we want to study is the space-time matter dichotomy as Niels explained and he told in the case of scalar-tensor theories. So I will briefly explain what we mean by scalar-tensor theories, and then the second part will be basically to establish some criteria of if this dichotomy really exists, how can we define it, how can we establish some criteria for being part of space-time and some criteria for being part of matter. Then we will design this in order to apply it for GR and prove that in principle, at least at how GR is usually framed, we can really talk about a dichotomy in terms of this criteria. And then the second part, which will be Alex called part of the talk, will be to apply the same criteria. So we narrow it down from GR, apply them to scalar-tensor theories, and discuss what happens there. Okay, so this is the strategy. And this is the path we will follow through the presentation. So let me just briefly introduce scalar-tensor theories, general cosmology. As Elisa explained very much in detail, we have a lot of data and we have a good background in theory, both convergent in the relativistic gravitational physics realm. We have a good understanding of many phenomena that have happened, we have observed during the 5 last decades, but also we have developed a very strong and technical background on the theoretical side of GR and modifications of GR, and we know quite well which theories can be possible in the extending GR and which not. So 2 examples of this is the CMB as this observational holy grail, where we can extract a lot of information about cosmology, and the second paradigmatic case is let's say the creation of many alternatives to GR, which could be a starting point of what is called the Brans-Dicken's or the Jordan-Brans-Dicken's theory back in the 60s as examples. So as philosophers, once a field is established, we are like very happy because then we can try to apply all the intuitions we have in the philosophical discussion to this kind of physics and see what happens. And so that would be basically the topic here, in particular to analyze space-time matter dichotomy inside the gravitational physics. So, of course, the first talk was already way more detailed than I will be. But the point here basically is that from cosmology data from the CMB, we know that basically almost all data can be described by 2 things. One is an almost homogeneous spacetime, or almost in the sense that we still need some perturbations, but usually they can be handled in terms of a spacetime dynamics. And then we would have some, on top of it, some matter fields. Some of them could have a quantum origin. That explains us everything else we need. And usually it's classified in baryonic, dark matter, and radiation. So one could assume that in this very sketchy description, everything consists of just spacetime or some matter. Now we know, as also Niels explained, that this is not the end of the story, and we require some additional explanation, in particular to dark energy, but also to inflation, which is also a case study in our case, that cannot be, at least the physics we know, explained only in form of the traditional matter fields. So now we use these two motivations to question whether the new ways of describing these two effects can still be inherent in that space-time matter dichotomy clear definition. So in our particular case, since Lisa showed this very big picture of thousands of modified gravity models, of course we cannot go through each of them because apparently even hundreds of physicists cannot cover all of them. So we just particularly will focus on what is called scalar-tensor theories. The scalar-tensor theories have their seed in what is called the Jordan-Brans-Dickens theory, where both Jordan on one hand and Brans-Dickens theory, Brans and Dickens develop it for different reasons. So Jordan's point of view was to start with some more general five-dimensional Kaluza line type theory, and from that reduce to a GR plus a scalar field. And Brans-Dickens had a different point of view, a more, let's say, phenomenological point of view, in the sense of still just take GR and modify it, adding a scalar field, in this case, using some kind of mass inspiration in the sense of trying to make the Newton's constant depending on the scalar field. But both of these point of views just converge on the same theory, which more or less has this form, where we have here the usual Ricci scalar as the GR contribution, but now multiplied by a scalar field, which would be the Newton constant in terms of the scalar field, plus some given matter, and then plus some dynamical of the scalar field, which would be given by this. So this is the original formulation of Brans and Dickens. Now, as a phenomenological side, people realized that it didn't have enough nice effects to really show any difference from GR. So of course, as it usually is the case, people try to generalize this theory to cover more cases and see then the phenomenological side of it. And it looked like a productive avenue. And basically, the most general way of defining it is, instead of having one scalar field here, one kind of function of a scalar field. And then instead of having these terms here, one kind of another function G. And then one can also even add a potential. Okay, so this is the biggest generalization to what we consider scalar-tensor theories in this case. And this is exactly the theory we will play with in the second part of the talk. Now, I just want to briefly say a bit more about the scalar-tensor theories, because it's true that Jordan was the first one of giving this picture of having a generalized theory. Actually, it is said that Brans and Dickens really gave the famous power to the theory, because at that time, maybe people were more willing to accept a modification to GR than actually a very big extension, 5 dimensions. But actually, I think today people really think that the way of proceeding is the other way around. So all these scalar-tensor theories on general modified gravity models would in principle be generated by some underlying fundamental theory, whatever your theory you prefer. And then from there, we will just have some scalar-tensor theories. And from there, we could maybe try to find explanations for, as I said, the dark energy case and the inflationary case. Okay, so now that is an introduction for scalar-tensor theories. So now we want to discuss the space-time matter dichotomy. In order to do that, I will first go step by step until we arrive to GR, which is the big elephant in the room, and then we can go to scalar-tensor theory. So the basic picture of the dichotomy would something as like this. So we would have two categories where we would have all the fields that we want to include, and we would be able in some way to classify them either in one category or another category. And you have to have a precise way, because if you have one field and suddenly you have any reason to believe why you could add it to one or to the other, then you are in problem. Also, another problem could arise that you could add it to one category, you could add it to another category, and there will be no contradiction. So this is the types of discussions we want to have. And in the clearest picture, we would have in GR a given metric, and then we would assign it to the space-time category, and then we will have a bunch of fields. You could have vector fields for QED, electron fields, fluids of cosmology, whatever other fields you want to think about. Doesn't have to even be fundamental. You can still classify into the matter category. Okay, so now we go to the part of trying to make this more formal and to have some, let's say, tools to play with. And the first one is to establish what do we want about to have for defining the spacetime category. And so the key point here is to think about the spacetime category as some list where you would include some kind of structure that you would require from some theory to be provided by, so that you can define then any other physical theory. So usually how it goes is that in order to define some given physical theory, you will need a notion of inertial structure, a causal structure, a kind of clock structure also to define some time. In case when you are talking about field dynamics, you would like to have some what I call good field theoretical formulation structure, which mathematical term would be, for example, global hypermobility. And so this kind of structure you always require the space-time to be. And then, of course, here you can add whatever you want. It could be spin structure, it could be any other structure. So in this sense, I call it like a list of desires that you would need in order to establish the space-time category. So usually this is very simple in our case, because for all the given theories that we know, and in particular electrodynamics, or any relativistic theory, kinetic theory, and so on, this amounts to just define, in case of relativistic theory, the spacetime category as containing a tuple minimum amount, which is basically a manifold structure, a covariant, affine structure, and then a metric. And this is the mathematical usual way. One proceeds with that one kind of any physical book like of TR, one will find that this is the usual definition of spacetime, of a spacetime. But one has, I think, one always to keep in mind that we were really thinking in terms of some underlying structure that we want to define, that it's not just a mathematical definition per se. Now, the matter category is a bit more tricky because, well, I would say it's a bit more tricky because people have less care about trying to precisely define what a matter category is. But in some way, one would always think about matter as terms of something that evolves in time, something that interacts with each other, and something that interchanges energy. Now, of course, I put all of this in quotes because we don't have yet a formal way of really saying what this means. But let us start with the first one, evolve, and I think more or less we do have a sense of what this means. So I define the first criterion for matter, which is basically that we can define matter, okay, as some localization of bundles, which would basically be the mathematical entity we require. And then we say that any material system, a set of possible interacting matter fields, is fully described by a given set of dynamical equations. So for any given set of matter that you provide to me, you will have to also provide to me some dynamical equations that make me realize how these fields evolve in time. Okay, so the paradigmatic case, for example, is let me assume I only have the electromagnetic potential in electrodynamics, and I give you some dynamical equations to it, and basically that's it. Okay, so in this case, it would be the famous Maxwell's equations, and then the only thing really I require is, of course, I have here another field, which is the source term field. I only will tell you that it's conserved, and with that, you can fully fix that system. Now, from this case, we can already learn something, because even though we have introduced the electromagnetic potential in terms of a matter, we have not said anything about the source term. Okay? And in this case, the source term just really acts as an extra term that you don't even know what it is about. So how to precisely say this is that we say that a given phi1 field, take the electromagnetic current, acts on a field phi2, being, for example, the electromagnetic potential, if we require information of phi1 to solve in a given region of interest the dynamical equation of phi2. So basically what we mean by this is that J acts on the vector potential, but not the other way around, because we will give, in this case, Maxwell's equation, we will give just the external source given to you without telling you what it's about. And so only by this dynamical equation, we cannot really say that A will act on J. Now, of course, one always doesn't think like this, and one really thinks that this electromagnetic current is built upon some another matter field, even though we may not know it. And then we, for example, in the case of relativistic fields, we can do that with a complex scalar field. So we would add another field here in our matter category, and then we will have the same equations for electromagnetic field, but then plus we would have an additional dynamical equation because that's what matter is. And then this current that we have here will be generated by the scalar field. So in this case, we can really say that A acts on phi and the other way around, because if you look at here, the dynamical equations for phi also requires A. So in that sense, we can now define what we mean by interacting, which is different from acting, by saying that a tuple of fields are interacting if this act definition is what we call an equivalence relation with this kind of set. So what we mean by this is that basically it has to be reflexive, symmetric, and transitive. And even though it sounds a bit abstract and useless, it will become useful afterwards. So basically the three properties, reflective basically means that of course the field acts on its own, in the sense that even in the sourceless case of the Maxwell's equations, we would require the initial value of the own electromagnetic potential to evolve it in time. Symmetric means that basically it's the act acted upon that Niels also introduced it in his talk. So basically A acts on phi, phi should also acts on A. And then a bit the more weird case is the transitive case, by which I put another example a bit more complex, where we have the electromagnetic case, we have another scalar, the same scalar field, sorry, complex scalar field creating the source. And then we have another scalar field here, this psi, which is not coupled to the electromagnetic case, but it's coupled to phi. And then what I say is that it interacts because this also acts on this, and this also acts on this, even though it's not coupled. And the more visual way of proceeding is just basically drive the Feynman diagrams of this system. And then you could have two phi fields creating two photons. This would be the usual case that if the electromagnetic interaction is going there. But we know that also kind of this diagram is possible, where you have the photon and this psi field, and even though it's not coupled, so this psi field is actually neutron field, it does interact with the photon, and we cannot neglect this. So the full system is interacting between each other, forming an interacting system. Okay. So in this sense, we would say that this system forms an equivalence class of interacting. So this is basically the third criterion to really motivate it. It's basically that for any given system of fields, if we can classify them into this interacting equivalence classes field, then the system is really a matter system, and each of these fields are matter fields. Okay, so this is basically how we want to fix this criterion. One can think of many examples I can later give you, for example, in cosmology or so, where one thinks, okay, once divided different ingredients, they don't interact with each other, they have equivalence classes and so on. So I think that for general matter theories that you can think, this can always be applicable. So here I put out a brief example. So we would have this is the example I added. And then one would have any other field that you would think of, and they could be interacting with each other, but maybe in the approximation you are playing with, the idealization, whatever, they don't interact together. So you can always create equivalence classes of interacting fields in this sense with this act relation that I defined. Now, this is here what we would say about evolving, about interacting. Now let's apply this to GR. Okay, this is now in special relativity, for example, it's quite trivial to use the above mentioned criteria to split between space and matter. But when we come to GR, we find the big problem, of course, that we know by the Einstein's equation that not only matter, all kinds of possible matter, does influence in this sense, and we would say it acts also on the metric by the Einstein's equation, and also the other way around, of course, because by the equivalence principle, we would say that any given matter field would couple to the metric in this case, for example, by the covariant derivative of the electromagnetic fields. And so we have really an interacting system here. So actually then the picture would be very confusing because of course every matter acts on the metric. So and then it also acts on all the matter. So it is actually part of matter. And that means that basically all systems are interacting with all systems. But for us, the worst part is that the metric then can also be included in the matter category, which is something that we wanted to avoid. Now, in order to the strategy to try to keep with the dichotomies, to actually try to add more criteria and see if we can solve this problem by stripping the dichotomy. So in order to do that, we focus again on GR because the problem was caused by GR, so hopefully GR can solve this. And then basically what we realize is the dynamical equations of both gravitational and electromagnetic fields are quite unusual to the usual any typical dynamical equations, in the sense that they also provide a way of classifying some effect in terms of being a gravitational or being, for example, electromagnetic or so on. So what we mean by this is that usually what we call gravitational effects are carried by some metric field. And what we say is that the dynamical equations have explicit dependence on matter fields only through the Spacetime tensor. This is the key point. We not only say that a metric has a given dynamical equation, but we, on top of that, say that if matter appears in the dynamical equations, it better be through the Spacetime tensor. Okay? And the analog case would be to say that matter appears in the Maxwell's equation through the electromagnetic current. And also we require that the Spacetime tensor is covariantly conserved. So here we can then add another criterion, assuming this, and then we say that any material system, this system will be endowed by a stress energy tensor that is covariantly conserved. So basically, GR provides us a way to say, okay, if you have a matter system, it better have a stress energy tensor because it will be the way it acts on the metric through the Einstein's equations. And then by this, we can also completely then eliminate the metric from part of the space, from the matter category. Why? Well, because one can take a counterexample, for example, the vacuum Einstein's equation, and one realized that one cannot construct a stress energy tensor applied to the system. So if G would be a metric, then it would not satisfy this criterion, and so on. So we have a way of discriminating the metric from being a matter criterion. So now we are back on track because we still can maintain the dichotomy. Now, just the last criterion, which will become relevant for the scalar-tensor theories, is basically that we try to unify in some way the requirement of the existence of the stress energy tensor with what the dynamical equations tell us about interaction. So, as I said before, the dynamical equations allow us, for a given matter system, to separate in equivalence classes. And each equivalence class is said to be interacting in itself. Now, if we assume that the stress energy tensor is really just, in some way, an energy way of transference of energy, this should be applied to this because systems that are interacting should transfer energy, but if two equivalence classes they will not be interacting with each other, they shouldn't transfer energy. So the way of formalizing this is we say that given the equivalence classes of interacting fields, each of these is endowed with a stress energy tensor that is covariantly conserved, and the full stress energy tensor, the one that appears in the Einstein's equation, is just the sum of each stress energy tensor. So basically, we would have this different equivalence classes, as I said before, and each of them has assignated a stress energy tensor, which is covariantly conserved. And this is the way to ask this notion of energy exchange in the case of interacting fields. Okay, so as I said, we are in the dichotomy of GR is still maintained, and now with this criteria, we go to the second part. We will reanalyze this case for the scalar-tensor theories.
Thank you. So what we have done so far now is Niels has already introduced the idea of having these criteria to separate what it means to be space-time, what it means to be matter. And now what Antonio has just done is he formalized these criteria. So we now have a very precise sense in which we can say whether some field is going to be part of space-time or deserves to be called matter. And so now we're going to apply this to the case of scalar tensor theories, which are also already been introduced, but which I will now make more precise in a slightly different way than what we've seen. So this is going to be quite a mouthful, so bear with me. So we define a scalar tensor theory as follows, and it's entirely equivalent to what Antonio said earlier. So a scalar tensor theory is a tuple consisting of manifold structure, metric, the scalar field in question, and some matter fields psi. And so these fields satisfy these two important equations. So first is a generalized version of the Einstein equation. and the other is a generalized version of the Gordon equation. And I will talk about the terms in a second a bit more. And for the sake of completeness, let me specify these other two conditions. We require that f is a positive function, and we require that the other dynamical equations for the matter fields only depend on the matter fields in a metric, but they don't depend on phi, right? And so we're working now at the level of dynamical equations because this is just more useful in what follows. And so we will be mostly concerned with analyzing these dynamical equations and not so much with the action, for example. And so primarily we'll be looking at the Einstein equation, the generalized Einstein equation. And let me give a brief overview of the term. So this is just the gravitational tensor multiplied by this scalar function f, which might depend on the scalar fields. And it's kind of like there's like a generalized Newtonian constant in front of it that may depend on the value of the field everywhere. Here, this is just the ordinary stress energy tensor, which depends only on the matter field phi, and the metric, of course. Then we have these kinetic terms, which won't be too important in what follows, and we'll set g equal to 1 because it's not going to play a really big role here. And then I want to highlight these two terms, which appear in the generalized version, and I want to stress the fact that they are second order derivative terms, and that will become important later on. And then there's this final potential term, which we will also set to 0 to make it more understandable. Okay, so now we've already seen what it means to have gravity in GR. But we need to extend this definition now accordingly, because we're working in a more general theory of gravity as well. And so it's very natural. We say that gravity in scalar tensor theory, we say the gravitational effects in scalar tensor theories are carried by a metric and a scalar field also now. And again, this important thing that it's dynamical equations can have an explicit dependence on other metric fields only through its stress energy tensor. And so what we're going to do now is we're going to analyze how to classify this scalar field that features centrally in scalar tensor theory, and see to which category it belongs or which it doesn't belong to. And to do so, we first ask, okay, so let's first ask the question, can phi be matter? And the argument that I'll give now will follow the structure of a proof by contradiction. We're going to assume that phi is going to be part of the matter category and see how this leads to a contradiction with the criteria that we've defined. And so conclude that it should not be part of the matter category. And so here I've written again the dynamical equations of the system in question. The first is just the Einstein generalized Einstein equation that I've just introduced. Only I've put this factor f phi to the other side. Because of the previous definition, right? Because of what it means to be gravity. So scalar, because if we assume phi to be matter, then it has to feature on the other side of the equation because the scalar field in the metric can only depend on phi through the stress energy tensor, right? And then there's the Klein-Gordon equation again. Here we have the conservation of the electromagnetic tensor, just Maxwell's equations, right? And then here we have the equation for the electromagnetic stress energy tensor. So this is the system that we're going to be analyzing. And so what we do now, just as in the previous examples that we've already seen, is identify the equivalence classes based on this relation act, right? And then so to see, okay, so what the matter fields that we have and which equivalence class are they part of? Well, we just have to see, do we need information of another field to specify its evolution? And so for the case of the electromagnetic potential, clearly we don't need, in these equations, we don't need to know precisely what phi is going to be doing. So it's going to be on an equivalence class of its own. And similarly, in order to specify the evolution of phi, we don't need any information of the electromagnetic potential. So it's also going to be on its own equivalence class. And so in order to satisfy these other two meta criteria, 3, 4, and 5, what we want is that to each of these classes, there's an associated stress energy tensor, each of which is conserved, and that the sum of these two stress energy tensors are equal to the full stress energy tensor. So this latter thing I said is basically just this. So we wanted the full stress energy tensor, like everything that's just on the right-hand side, the generalized Einstein equation, is equal to the two separate stress energies corresponding to the equivalence class, right? So this one is the phi one, which should correspond to this one, and the electromagnetic one, oh sorry, the other way. So the electromagnetic one should correspond to this one, and the phi one should correspond to that one. But what we see is that, yeah, so if we want to have this this condition satisfied, that the sum of them is going to equal the total one, then we're going to get into this tricky situation where these stress energy tensors are not conserved, so that either one of the criteria has to fail, which I won't show in detail here, but point is that this implies a contradiction, and so we have to question our initial assumption that phi is part of the meta category, and so we have to say it's not part of the meta category. Right? And then there's the second argument that I want to make, where we ask if phi can be matter, and well, to specify, okay, to say how this goes, let's consider again the Einstein equation. And now what you should notice that this is a dynamical equation for the metric and for phi, and that these two, so that phi and the metric are mixed together in this equation. And what I mean by that is that we see second order derivatives of the metric, which are implicitly present in the Ricci tensor and scalar, and we have second order derivatives here of the scalar field. And so, kind of motivated by the idea that that to have an initial value problem that we can actually solve. Yeah, you can see that these two quantities are kind of mixed, right? And so it appears that phi is part of the same physical system as the space-time metric. These two, so the scalar, so the points of the scalar field phi and the metric are kind of mixed together through these higher order derivative terms, and so we see that phi is kind of like a space-time is bound up with the space-time entity, so it's kind of space-time itself, right? But this is maybe not the full story, because we might be able to simply rewrite this system in a different way. We can reduce it maybe to another system in terms of other variables in such a way that we get rid of these second order derivative terms. Then this problem might not appear even. And well, it turns out that we can indeed do this. And this we do by means of what is called a frame transformation. So this is our original variables, the original metric, and the original scalar field phi. And we move to a new frame in which we denote the metric with a little tilde on it, and we denote the transformed new scalar field by sigma. And so to get to this new frame, what we do is we take two steps. The first step is that we do a conformal transformation on the metric. So that just means basically a field-dependent rescaling of the original metric by this factor omega squared. And in this, we take a specific conformal transformation to go to the specific Einstein frame. And this is specified by the fact that we take this this factor omega squared to be equal to our scalar function f, that is part of the definition of our scalar tensor theory, right? And what we also do to simplify the equations is that we do a redefinition of the scalar field. So first it's phi, and later we will call it sigma. And well, it's defined as follows. You can view this as kind of a reverse engineered expression to simplify what we're getting, what we want to be getting, namely to get rid of these second order derivative terms, right? And so I'll just quote the result here. So for the general Einstein equation, we get this equation where I only want you to notice that indeed these higher order derivative, the second order derivative terms have disappeared. And we get a new version of the Klein coordinate equation as well. So in this frame, we kind of don't have this mixing property between the scalar field and the metric, right? And so what we want to be doing is go through these steps again to see now for this new scalar field sigma, whether we can classify it, or whether we should classify it as spacetime or as matter, and see how the analysis holds up. So first, let's ask the question if sigma is part of spacetime. Well, recall that from the definition of this frame transformation, what we got is that the old metric is equal to this factor times the new metric. And so, so if we're going to have matter in this redescription, in this Einstein frame, then it's going to serve as a spacetime that is given by both sigma and the new metric. And so, well, it's quite clear then that sigma is a part of the spacetime structure in order to describe the inertial structure, the causal structure, that kind of thing. So, in conclusion, sigma satisfies the spacetime criteria here. And then we ask again, can sigma be matter? And we're going to try to play the same game as before. So again, we're going to be assuming, okay, let's see what happens if we assume that sigma is part of the matter category. Now, here's again the new Einstein frame, Einstein equation. And we split it in two cases. And in the first case, we assume that our matter field is conformal matter, which intuitively kind of means that it's in sort of invariant, or that its solutions are invariant under conformal transformations. And again, we're going to identify the act equivalence classes, and we find that in this case, in the case of conformal matter, that these are given by, so that sigma is going to be on an equivalence class on its own, and the conformal matter field is also going to be on an equivalence class of its own, just like we had before, kind of. But this time around, we find that the equivalent. So okay, so again, what we want is that each equivalence class has an associated stress energy tensor. That the two of them, when we add it together, is the full stress energy tensor, and that each of them is separately conserved. And we find that actually in this case, I'll just quote the result, we can do this. So we have this first stress energy tensor corresponding to the first part of this equation, right? Which corresponds to the matter field, of course, and with the second stress energy tensor corresponding to which is the rest of this equation, basically, that's corresponding to transformed scalar field. Each of them is going to be conserved, and they're going to add up to the total stress energy tensor, which is going to be conserved also by Yankee identity, of course. So this case works. And let's consider the second case where psi is non-conformal matter. Well, what happens in this case? We have a single act equivalence class this time. So both of them are going to be part of the same class. So we only need to find one stress energy tensor, which is conserved, corresponding to both of these quantities, and equal, which is trivially equal, of course, to the total stress energy tensor, because this is the only matter equivalence class that we're going to be having. And so it's going to be conserved, and so everything is going to work out fine as well. So the conclusion is sigma being matter is not in contradiction with the matter criteria. So for all we know, sigma might be part of the matter is, or I should say, sigma is as much matter as anything else. Okay, so now there's maybe a little last section, which is basically revolves around the question, what do we make of all this? And I would say this is very, very much work in progress of this project. And so I'll be quite brief also, I think. So let me first look at the conclusion that we can draw from everything that we've done so far. The main conclusion, I guess, that we want to draw first is that the categories of space-time and matter are frame dependent. And so let's summarize the results that we found in each of the frames. The Jordan frame is the first frame, and the Einstein frame is the transformed frame. So in the Jordan frame, we have the following space-time and matter categories. So in the space-time category, we have the scalar fields, because we showed by contradiction it could not be in the matter category. We have the metric here, of course, and we have the metric fields on the other side. And then in the Einstein frame, we kind of have two options that seem to work, right? If we suppose the space-time matter dichotomy, of course, we have two options. And in the first option, we have that sigma satisfies all the space-time criteria, so it is part of space-time. On the other hand, we saw that sigma being part of the matter category also doesn't lead to any contradiction, so we might as well put it in the matter category. So if we believe that there is there's a space-time matter dichotomy, so everything should be either in the one or in the other, never in both, but never in either, then well, these are the two possible pictures that we could have here of the Einstein frame. And so indeed, conclusion is that these categories of space-time and matter depend on whatever frame you're in. So what do we make of this? Well, first there's the question of whether the Jordan and Einstein frames are empirically equivalent, which I believe is still, there's some debate about this in the literature still, but there seems to be pointing in the direction that they are empirically equivalent. So we bracket this question and continue under the assumption that they are empirically equivalent. And then the remaining question becomes, how do we further characterize this equivalence of the frames? What do we do with it? And this seems to be embedded in a larger philosophical discussion between interpretationalist and motivationalist strategies. And so, okay, so what are they? So the interpretationalists, when talking about symmetry, and symmetries are here, I would say quite broadly construed as maps that preserve structure, things like isomorphism, a change of variables, change of coordinates, something like this. And so the interpretationists say, well, symmetries are just redescriptions, even if in one of these descriptions, even if in these descriptions there are say different things about metaphysics, so something being there, something not being there, still they are just redescriptions, right? And what these motivationalists say is, well, no, what these symmetries, that merely motivate us to find a symmetry invariant version of the theory, so a reduced version of the theory in which you can get rid of excess structure, right? You can kind of excise that. Okay, so how does this translate to the scalar-tensor theory case that we've been considering so far? Well, what would the interpretationists say about this? Well, they think the symmetries are just redescriptions. So they would say Einstein and the Jordan frame simply represent the same state of affairs. But this would imply that there's no objective fact of the matter about whether the scalar field is part of space-time or whether it's part of matter, because this is a frame-dependent thing, as we've seen. And so in this interpretation, the space-time matter dichotomy breaks down. As for the motivationalist, I would say that well, the symmetries, so the frame symmetries that we see, this should motivate us to find a symmetry invariant version of the theory, right? And what would that look like? Well, that would be one that is invariant at least under conformal transformations, right? And so light particles we know to be invariant under conformal transformations, but this is of course not enough, right? Because we're going to have matter particles as well. They're going to be traveling time-like curves, and so it just won't be sufficient to have a reduced version that only focuses on conformally invariant stuff. So we wouldn't know how to find yet a conformally a reduced theory. And then there's maybe another option that kind of transcends the debate, which is called fundamentalism. And this says that based on some metaphysical or theoretical explanatory criterion, one of the frames can be viewed as privileged. We can say, well, in reality, it's the Jordan frame that is the correct one because it serves better in explanations, or because we like its metaphysics better, something like that. And so one argument that could be made is that, as we've seen in the first part of the talk, that usually the fundamental theories produce a theory in the Jordan frame. So that could be an argument in favor of that. On the other hand, the Einstein frame also clearly has its virtues, and it's also used a lot because it's, well, you get rid of these higher order derivative terms, so it's much easier to analytically solve your system of dynamical equations. So I think the jury's still out. I don't think you can very easily say that one of the frames is privileged. There's a whole lot of debate about this still in the literature, so it's definitely not a clear-cut case. So the question is, what can we still say? How do we move forward with this? So we've seen first major conclusion was that the categories of space-time and matter are frame-dependent. But something that is not frame-dependent is the gravitational effects, which we've defined before. And so what we could say, or what we could maybe more appropriately do, is classify these fields according to whether they're gravitational fields or whether they're non-gravitational fields. I'd like to end it there. Thank you.